A client met his banker to discuss opening a restaurant in a busy airport. In us, he found a partner that understood the importance of reaching for the sky. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Mac. A lifetime of hard work. Children laughing in the kitchen. Family photos on a restaurant wall. A legacy that lives on. It all comes from the power of a conversation. Like the one Tommy Hall had with First Horizon Bank about taking over his father's Charleston-based restaurant business. Now the table is set for a whole new generation. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Tommy. First Horizon Bank, member FDIC.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you for joining us on Space Nuts. It's so good to have your company. I'm your host, Andrew Dunkley, and I hope you're well. Today's program's a little bit different. We will not be venturing into the universe through new knowledge that's been published or talking about space rocket launches that have happened in recent times or asteroids that have, hit us and killed us all. Don't think that's happened. What we're doing today is dedicating the show to the audience. Once in a while, we throw it over to you to throw at us some of the questions you want answered. And so that's what we're going to be doing today. Questions about the ultimate fate of the universe. I think I know the answer to that one, and it's going to happen next week. Cepheid variables is a question we've received. What is that, and what does it cost at the supermarket? Can we use magnets to protect spacecraft heading to Mars, or anywhere for that matter, I suppose? Can asteroids that come close to Earth change our orbit? And a question we've received from Paul in Queensland, and he's put it all in song. And I think it's a ukulele that he's backed up with. It's brilliant. We'll give you that. And the movement of stars in our galaxy, all of those questions we will answer today. And if we can't answer them, we'll make it up on Space Nuts. And joining me, as always, is Professor Fred Watson, Astronomer at Large. Hello, Fred.
Hi, Andrew. We're pretty good at making things up, you and I, actually.
It's one of the things they teach you in journalism school.
Make it up.
Yeah, the segment is called "Never Let the Truth Get in the Way of a Good Story."
Yeah,
it's everybody's favourite thing when they go to school to learn about broadcasting and journalism. Yes, we've got a whole bunch of questions to get through today, Fred. So we might as well get straight into it if you're ready.
Yep.
Okie dokie. We'll go first to Mark.
Hello, Space Nuts. Martin Berman Gorvine here, the science fiction writer who asked you recently about the non-existent luminiferous ether. Today I'm wondering about the ultimate fate of the cosmos. Will it continue expanding infinitely until everything is very cold and very thinly spread, as imagined in classic science fiction tales such as John W. Campbell Jr.'s Night and my own Tricky Dick Nixon and the Heat Death of the Universe, which is available on Amazon? Or is there any chance that instead of freezing to death, we're all going to crunch up in a super hot collision as everything snaps back like a universal rubber band and collapses into a singularity and maybe explodes again in another big bang ad infinitum? It's my impression that the cold soup scenario is now thought to be more likely, but what is the real evidence? And might opinions change again? Thanks for taking my question.
A great pleasure, Mark. Lovely to hear from you again. And yes, it's one of the most popular questions that gets asked of astronomers. Fred, what's going to happen to us all? Is the end nigh? Well, probably not, but it's going to happen eventually. But how will it end? Will it just become a big frozen ball of nothing, or will it, will the Gib happen, the reverse Big Bang, and just crush in on ourselves in a flaming end? It's a question that surfaces quite often.
Yeah, and actually, Mark has already given us the answer in the title of one of his novels, which included the term "the heat death of the universe." And it's interesting that was a term that was popular when I was a youngster. Kind of before I became an astronomer, people talked about the heat death of the universe.
That was
the
back
idea
in the late 1800s, wasn't it, Fred?
It wasn't that long after that, no. The late 1800s always seemed quite recent to me when I was growing up, believe it or not. That's more to do with where I grew up, I think, which had its feet firmly planted in the late 1800s, including the school I went to. Anyway, all of that's irrelevant, but it essentially the heat death of the universe is the idea that the universe just cools down and basically fizzles out. So for a period during the 70s and 80s, there was a much different idea, a more popular idea, that maybe the universe, which was known already by then, of course, to be expanding, that was discovered in 1929, that the universe might slow down in its expansion because of the gravity of everything within it, and eventually stop expanding and start collapsing on itself to produce what you and I have discussed before, the Big Crunch, which was also christened by Brian Schmidt, the Gnab Gib, which is the Big Bang backwards. Fantastic stuff. I love to get that in anything I can when I talk about it, the Gnab Gib. So the idea was that, yes, maybe it would collapse back to another singularity, which would sort of bounce. Maybe the expression "the big bounce" was sometimes used, so that you get another expansion from this rebound of the universe. What put the nail into the coffin of that idea, the final nail, was once again Brian Schmidt, the professor of astronomy as he then was at the Australian National University. Now in fact it's vice chancellor. So the discovery made by Brian's group and another group in the USA, led by Saul Perlmutter, those two groups independently demonstrated that the universe is expanding at an ever increasing rate. So it's accelerating. And we think that's because of dark energy, which we don't understand. And so what we've got now is a scenario where, to the best of our understanding, the universe will simply continue expanding at an ever-increasing rate, unless something changes. But what that might be, we have no idea.
Maybe bumping into another universe.
Well, that's the sort of thing. But at the moment, that's so far beyond our knowledge horizons that we really can't do anything about it, or even build it into our ideas. So at the moment, the idea is, yes, that the universe will continue to expand at an ever-increasing rate. And so the fate of the universe is not pretty. I might actually make it easy on myself by reading from the new book, Space Warp, because I've got a little section on the fate of the universe, which says, if the accelerating expansion continues as it's going now, there will come a time billions to trillions of years down the track when distant galaxies start disappearing. That's because the light leaving them will never reach us, since the space between them and us is expanding too fast. Astronomers in the far distant future will only be able to study our Milky Way galaxy and its fellow members in the local group. To them, that will be the whole universe. And to make matters worse, the universe's hydrogen supply will have been exhausted, so no new stars will be formed, while the existing ones will eventually die and turn into black dwarfs or black holes. But even that isn't the end of this dark and gloomy story. This is to cheer up the youngsters and read it.
This is a children's book,
yes,
isn't it?
It is. There's better news after the end of this section. Eventually, space will be expanding so rapidly that galaxies, stars, and planets won't be able to resist its power to tear things apart. They will be spaghettified as if they were falling into a gigantic black hole. And the final insult, as it is an event usually called the Big Rip, in which atoms, subatomic particles, and perhaps even space-time itself will disintegrate. As I said, it's not pretty and basically has all the hallmarks of a gigantic temper tantrum. Not nice behavior for a polite universe. Fortunately, it is so many billions or trillions of years in the future that it really doesn't matter.
And who knows where humanity will be then if it exists at all.
If it exists at all, that's right. Yeah.
So it's not going to be a pretty end, Mark, I'm afraid to say.
As far as we know.
As far as we know. But I suppose the thing that is difficult to get my head around and most people's heads around is how could the universe possibly continue to expand at an accelerating rate? It just doesn't seem logical.
It's yes, and dark energy isn't logical, which is why we really don't understand it. So the idea of dark energy is that it's a product of space itself. So the more space you've got, the more dark energy you've got, and that pushes it, apart even faster. So it's like what you might call a positive feedback. It just kind of keeps on going and eventually produces effectively an exponential expansion.
It's like a giant fusion reactor. It just keeps feeding itself.
Yes, except there's no fuel and no need to convert anything into anything else. It just comes from space.
Yeah, it's so strange.
Work
it's
that
so
one
strange.
out.
I can't. You can't figure it out. What hope have I got, Fred?
So it's possible that our idea of what dark energy is like is wrong, and that it's not a property of space itself, that it's some other fundamental force. And one that people talk about is called quintessence, a fifth fundamental force. If that's the case, then it might behave in a different way. It may get quenched when the universe gets to a certain size, or who knows what could happen.
Yeah.
But based on what we know so far, the end I've described is what might well happen.
And somewhere along the line in that process, it's going to get very cold and dark, is it not?
Yeah, because there's nothing left. Stars eventually die. They all die out. There's no hydrogen left to form new stars. So it becomes cold and dark.
And so it's just going to be a whole bunch of dead rocks floating around.
More or less. That's right. Getting further and further apart. It's
How
boring,
exciting.
Yeah. The Big Rip's a lot more exciting.
It is.
Everybody would be having their Big Rip party. Sorry, the Big Crunch. I beg your pardon.
The Big Crunch
would be a lot more exciting. Yeah.
But at least we all get to go to the restaurant at the end of the universe.
The universe, exactly.
Exactly.
Right.
Hitchhiker's Guide to the Galaxy, for those who are going, what on earth is he talking about? In fact, people say that to me every week.
Yes, whether you're talking about that or not.
Indeed. All right. So there you are, Mark. You asked, and you probably don't like the answer, but nothing much we can do about it at this point in time. And you did say that the space-time might unravel, which means time would end, wouldn't it?
Well, probably, yeah. It probably falls to pieces. So as time gets fragmented into little chunks. Now, how do you deal with that? I have no idea.
You have to wear 50 million watches, I suppose. I don't know.
Yeah.
No idea. No idea. Okay, thanks, Mark, for the question. Now let's move on to our next inquisitor. And this is Paul from Pennsylvania.
Hello, Fred and Andrew. This is Paul from Pennsylvania. I have a question about Cepheid variables. I know Leavitt discovered that they were variable, and Hubble used them to discover the distances to galaxies. I was just wondering exactly how that worked.
Oh, that's it.
Never seemed to be able to get a straight answer on that.
Right.
Thank you. Bye.
Cepheid variables.
Yes, they are they're fundamental in our understanding of the distances to galaxies, particularly. So, and it goes right back to Hubble's time, exactly as Paul says.
One of your old classmates, wasn't it?
I wish. He was a bright spark, that lad.
Very.
But it was actually a woman who discovered the fundamental issue here back in 1908. Henrietta Swan Leavitt, who Paul mentioned, she looked at many thousands of stars in the Magellanic Clouds. These two, as we now know them to be, nearby dwarf galaxies. And the thing about studying variable stars is if they're all in one place, as these were in the Magellanic Clouds, then you know that they're all effectively at the same distance, which we now know is, I've forgotten these numbers, 165,000 light years for the Large Magellanic Cloud. So they're all the same distance away. And so any changes in their brightness is intrinsic. It's not caused by it coming backwards or forwards or anything like that. They're all sitting in this Magellanic Cloud, and they're all varying with different brightnesses. That's what a variable star is. It's one whose light output varies over time. So she could watch these things and make the observations. And the discovery that she made was that Cepheid variables, first of all, are periodic. Their variation in light actually, it's regular, but they don't all have the same period. So their periods range typically up to 60 days or something like that. Somewhere between 10 and 60 days will be a typical time for the period of a Cepheid variable star. But what she discovered was that the ones that vary over longer timescales are actually brighter. And they're brighter intrinsically because they're all at the same distance. It's not a distance effect that she's confusing it with. The longer period Cepheids are brighter. And Henrietta Leavitt was able to essentially plot a diagram that shows the relationship between the period of variability, how it goes up and down, how long it takes to go through one cycle, and the brightness. And it's called the period luminosity diagram. It's actually the fundamental thing. So what it means, Andrew, is if you find a Cepheid variable in the sky, all you've got to do is to measure its period, how long it takes to go through one cycle. You then look up Henrietta Leavitt's diagram or its modern equivalent, and that tells you how intrinsically bright it is. And if you know its apparent brightness, as we observe from Earth, then that gives you its distance very accurately. And that's how it works. So it was when Hubble detected Cepheid variables in the Andromeda galaxy, which he would have called the Andromeda Nebula because he didn't know it was a galaxy, he was able to plot the distance very exactly. In fact, they got it wrong because there was an error in the calibration of the Cepheid variables, but that was fixed later. So that is the step, and that's what allows you to start measuring the distance to galaxies. It's that fundamental, step in the what we call the distance ladder. And actually, it is the reason why the Hubble telescope was built and launched and used was to make very accurate measurements of Cepheid variable stars in other galaxies to work out what the calibration is for distant galaxies.
The only thing I can think of in that regard is with everything constantly moving, wouldn't there be constant variation in the calculations and the results, or am I thinking out?
Well, things are moving, but only on the distances through which they move are tiny compared with the distance away that these stars are.
Right.
So it doesn't actually make any difference to the brightness. If they were whizzing away and their distance was changing by a factor of 2 or 5 or 10 or whatever over a short time, yes, that would make a difference. But no, it was doing them in the Magellanic Clouds that was the clincher, because you know that they're all 165,000 light years away. Yes, the clouds have got, or for the large cloud, the clouds have got their own thickness, but it's tiny compared with the distance to it. So very, very clever stuff.
Yeah, fascinating. Way beyond my pay grade, definitely.
Well, it's probably beyond Henrietta's as well. So, because she started off as one of these computers, one of these people who just measured the brightness and positions of stars. But she became a pivotal figure in 20th century astronomy.
Yeah, quite astute by the sound of it.
Absolutely.
All right. Thank you for the question, Paul. Great to hear from you, and nice to nice to get something completely different. We've never really discussed that before, so good for you. You're listening to, and if you're a YouTuber watching, I don't know why you'd want to see our faces, this Space Nuts with Andrew Dunkley and Professor Fred Watson. Let's take a little bit of a break so I can tell you about our sponsor, NordVPN. Now, as a Space Nuts listener, there is a special opportunity only for you to get NordVPN, the best VPN service available in the world at the moment. They are offering 73% off a 2-year plan if you crunch the numbers. Basically, they're offering 2 years plus 4 months free if you sign up to the NordVPN service. And it is very worthwhile because not only do you get a massive discount for being a Space Nuts listener, you get one of the best in the business looking after your security. They will shield your browsing from cyber criminals and cyber surveillance. All the data you send and receive online travels through an encrypted tunnel. So there's no way anybody can get their hands on your personal information. And let's face it, with all the scams and lowlives out there trying to get hold of your money through your online activity, it makes sense to provide some layer of security. Well, this is the best layer of security you're going to get. It works on all kinds of platforms: Windows, MacBook, Linux, Android, iOS. It works on all of them, and it works seamlessly. You can secure up to 6 devices on a single account, and that even covers your smart TV, which, that's pretty impressive. And you've got access to the global internet. So what you can do is change your IP address and enjoy the internet experience without borders. It's a pretty simple process. There's all sorts of reasons to choose NordVPN: 24-hour, 7-day-a-week service and assistance. Online freedom is what they offer you. Reliable encryption, quick connection. In fact, sometimes your speed through their VPN service is faster than your existing service, which is quite amazing. And I know it happens because I've seen it myself with when I've connected NordVPN through my internet service provider, and it is the fastest VPN on the planet. Over 5,200 servers worldwide. So you should be able to log in anywhere, anytime to access whatever it is you need, or just have it running in the background during your day-to-day business, knowing that you're fully secure. So if you'd like to take advantage of the service as a Space Nuts listener, there's a special URL, nordvpn.com/spacenuts. That's nordvpn.com/spacenuts. Sign up today. You'll get a 2-year plan and an extra 4 months for free. That's a pretty good deal. nordvpn.com/spacenuts. Now back to the show.
Okay, we checked all 4 systems and skiing with a go.
Space Nuts.
Now, have you visited our website? It's very worthwhile because we spent next to nothing on it and it doesn't really do much. No, I'm not kidding. Well, I am kidding. spacenutspodcast.com. But we also have an alternative URL, spacenuts.io. I don't know why we did that. I mean, we confuse people enough. Now we're giving them multiple URLs. But it's okay. There's plenty to do there. Of course, we've got our shop. You can visit the shop. You can get quite regular and up-to-date astronomical information through Astronomy Daily. You can leave a review. You can click on our supporter link and find out how to support Space Nuts. There are all sorts of things to see and do. And, we're getting more and more material on there every day. spacenutspodcast.com if you want to check it out. Now, Fred, we better keep going because we've got another bunch of questions to get through. And this one comes from Abe.
Hey, guys. This is Abe from Boise, Idaho. I love your show. And I had an idea for the Mars trip. Why can't we bring the magnetosphere that protects us on Earth? Can we create something like that for the spacecraft using magnets instead of heavy lead shielding or water to protect from the cosmic rays? Thanks. I love your show. I listen to you at work all the time. You guys are awesome.
Thanks, Abe. So great to hear from you, and hope all is well in Boise, Idaho. We've talked before about long-haul travel in space, and going to Mars is going to be a big challenge. The exposure to cosmic radiation being one of the many pitfalls of traveling, and protecting astronauts from that kind of exposure. Yeah, he mentioned lead. We've talked about water in the past, but these things are very heavy and difficult to put around a spacecraft, I imagine. So magnetos or magnets, is that a possibility?
It is. It is a possibility. And in fact, Abe is right on the money with his idea, because research has been going on this sort of thing actually since the 1960s. But it's recently taken a big step forward. So back in the 1960s, the idea of magnetic protection from radiation for space travelers, say on their way to Mars, was thrown out because the suggestion was at that time that you'd need to shield a volume of space greater than 100 kilometers across. You'd need to generate a huge magnetic field that stretches out into space 100 kilometers and needs enormous electrical power to maintain it. So that was the old idea, and that's why it was thrown away. But there's recent research which actually come from the UK. It's led by somebody called Ruth Bamford, who's at the Rutherford Laboratory, which is not far from Oxford. It's at Abingdon, if I remember rightly. It used to be one of the sister organisations to the Royal Greenwich Observatory, and I worked there 100 years ago. The Rutherford Laboratory is a high-energy physics laboratory. But Ruth Bamford of this laboratory has recalculated this because and I'm quoting here from a Physics World article. According to Bamford, these previous calculations are inaccurate because they assume that the solar wind plasma behaves like a normal fluid. Decades of research on nuclear fusion have instead shown that plasmas are subject to all sorts of turbulent behavior not seen in normal fluids, and that furthermore, this turbulence can occur on roughly human scales. So the researchers believe it's possible to exploit this knowledge of turbulence to create a much smaller protective bubble, and have confirmed this belief first through computer simulations and then in a laboratory experiment. The latter involved injecting a supersonic plasma into a 1.5 meter long vacuum vessel lined with magnetic coils with a target magnet placed at the far end. And it goes on. This is courtesy of Physics World. So the bottom line is that there is active work going on exactly this topic at the moment. And actually, there was a nice quote. I don't know whether I can find it from Ruth Bamford, which struck me. She made a comment that I thought, oh yeah, here we are. Getting in a tin can with a rocket on your back and flying to Mars is never going to be a safe thing to do. So that's Ruth's comment, and I think that's perfectly true. But what's coming out of this work is the kind of power levels that might be needed to protect the spacecraft, and it's actually quite manageable. They're suggesting somewhere between 1,000 watts or thereabouts and 5 kilowatts. Now that's basically a good-sized electric heater in your living room. Just to put a yardstick on that, the solar panels or the solar arrays from the International Space Station, they generate something like 120 kilowatts. So, if you had that sort of capability, your magnetic protection would be quite feasible. It would be a small drain on that sort of power supply. So, really interesting question and interesting work that is ongoing as we speak.
There you go, Abe. You're right on the money. On the money. So, it's obviously And it sounds like it'd be very cost effective too.
It might well be, yeah. It may turn out to be something pretty impressive. Yeah.
Good stuff. Okay, thanks, Abe. Lovely to hear from you. And we'll move now to Brazil.
Hey, hello, Space Nuts. This is Claudio. I'm from Brazil. I have a question about black holes. Oh, no, just kidding. Actually, it's kind of a black hole humor. No, my question is actually about some episodes ago you were talking about the solar expansion and well, the fact that in a few million years the sun will be bigger and bigger and bigger, and we will not be that comfortable if we stay where we are now. So probably we would have to change the whole planet a little bit further. So I remembered some time ago I heard this idea of, I don't remember exactly where it was, but well, we would be capable eventually of changing asteroids' orbits in a way that they could pass on the right side of Earth, and then using the gravity of these asteroids, we could maybe, using little steps, change Earth's orbit so that we could go further and further and further from the sun. Of course, this would take millions of years and probably thousands of asteroids, but it's kind of a nice idea. Maybe we have time, probably. Like the sun is not going to expand that fast. So I would like to know what do you think about this idea? Do you think it's maybe possible in a far future to do these kinds of things? Thank you, and keep the great work.
Thank you, Claudio. Well, great to hear from you too. It's good to have an audience in Brazil. Now, using asteroids to change the orbit of the Earth to keep us moving away from the expanding sun, feasible?
No. Claudio, a great question and a great idea too. But the problem is the raw material that you're equipped with is totally inadequate to do anything to the orbit of the Earth. If you added up all the asteroids in the main asteroid belt, which is by far the biggest congregation of asteroids in the solar system, add their masses all together, what you get is 4% of the mass of the moon, not even 4% of the mass of the Earth. Now, the moon's only an 80th of the mass of the Earth. And you're talking about 44% of that. And actually, a third of that total mass is Ceres, the biggest asteroid, the dwarf planet Ceres. So even if you could grab Ceres and steer it around in the right kind of orbit, it would have effectively zero effect on the Earth. The Earth is much more massive than the whole of the asteroid belt put together. And it's good to have those comparisons. We tend to think we asteroids are quite high on our agenda. We're very conscious of them and we think about them a lot. But we don't often think about their mass in terms of the mass of the planets, but they're basically much, much, much less. So it's not something that could be done. It's hard to know with an object the size of the Earth, even with the most mega scale engineering that you can imagine, it's hard to know how you would shift its orbit artificially. Objects as massive as a planet they don't move that easily.
There was a really bad I think it was Japanese or Korean sci-fi that I watched recently where Earth needed to be moved because something dreadful was going to happen to our solar system and they had to move us out past Jupiter or something. So they just strapped like tens of thousands of rockets to the Earth.
Good.
Yeah, that wouldn't work either. I did read a sci-fi novel some years ago called Nemesis, I think it was. I don't know who wrote it. It might have been Robert A. Hyland or something. But,
if it's the one I'm thinking of, I can tell you it's Bill Napier, who's a guy I used to work with in Edinburgh. Bill Napier. In fact, it's on these bookshelves, isn't it?
Oh, okay. Well, maybe that's the one, but I think the basis of it was that Earth was going to be hit by an asteroid, and they worked out that they could make it miss by using gravity through a spacecraft of some kind to just slowly divert it over time.
That's right.
So your concept does have merit, Claudio, but not on a planet-like scale. I think would
that's
be
right.
fair to say. Yeah, all right.
That's correct. Yeah.
Nice to hear from you. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Introducing Carvana Value Tracker, where you can track your car's value over time and learn what's driving it. It might make you excited.
Whoa, didn't know my car was valued this high.
It might make you nervous.
Uh-oh, market's flooded. My car's value just dipped 2.3%.
It might make you optimistic.
Our low mileage is paying off. Our value's up.
And it might make you realistic.
Car prices haven't gone up in a couple weeks. Maybe it's time to sell.
But it will definitely make you an expert on your car's value. Carvana Value Tracker. Visit Carvana.com to start tracking your car's value today.
Space Nuts.
Now, if you'd like to become a patron and support the Space Nuts podcast financially, we would be thrilled. It's totally up to you, of course. I haven't really talked about it much lately, but it's an opportunity for you to put a few dollars into the tin can that keeps Space Nuts humming along. And plans start at $4.50 a month. And you can do that through patreon.com, or you can do it through Supercast, or you can do it through any number of options, which you'll find on our website, spacenutspodcast.com. There endeth the spruik. Now, Fred, let's move on to our next question. This one comes from Richard.
Hello, Andrew and Fred. This is Richard from South Salem, New York, just north of New York City. Love your broadcast. And I have a question that's always troubled me or perplexed me, is the actual movement of stars in our galaxy. I know even though we have a spiral galaxy, all the stars don't move as if it's a big swirl to the blue Danube. But stars are going in all different directions. There are streams of stars from all gobbled up galaxies. There are groups of stars that formed at one time and are moving in the same direction, like the Ursa Major movement group. Is there a clear way of understanding? Yet at the same time, I understand there really is an orbiting around the galaxy that takes our sun about 200 million years to make a full route. So is there rhyme and reason to the movement of stars in the galaxy, or are they all moving in different directions, buzzing around this way and that? Thanks a lot. Look forward to your answer.
Okay. And thank you for getting in touch with us, Richard. Hope all is well in your little part of the world. Actually, it's a big part of the world. But movement of stars, I think God was playing snooker and went bang. That's what I think happened.
Almost that sort of thing. It's a great question and sort of goes to the roots of how we understand the motion of stars in our galaxy. And in fact, really goes back, historically, it goes back to the time not long after Hubble worked out that spiral galaxies were very distant objects, and that we probably lived in one of those as well. Because at that time, that was not known. It was, assumed that we lived in a disk of stars. We knew we weren't at the center of the disk. Harlow Shapley proved that in 1919. But the motion of the stars in the galaxy, that was actually kicked off by Dutch astronomers. Jan Oort was the best known one, well known today for the Oort cloud, where the comets come from, the reservoir of comets. But Oort and one of his colleagues, I can't remember who it was. I'm ashamed to say that, but never mind. I did write about it.
His name is clearly Nort.
Yeah, Oort and Nort. Actually, I think it was. It's on the tip of my tongue. It was somebody like Hertzsprung, but it wasn't him. Anyway, never mind.
This is why they called. This is why they call you Fred. So you
remember the damn name. Yeah. And what's it short for again? I can't remember. So yeah. Anyway, Jan Oort, and the reason why his name is the one that comes to mind is because what he did was he looked at the motion of stars in the vicinity of the sun. And if you think about the fact that these stars are all swirling around the center of the galaxy, he actually teased out from the individual motions of the stars what the underlying flow was. So, Richard's right in the sense that the stars do have their own individual motions, but it's part of a bulk motion as well. So they've got what we call proper motions, which is their motions as seen from Earth, but they also have real space motions, which you can relate to the kind of average motion of all the stars at our distance from the center of the galaxy. And this was what Oort did. And it's why we have what are called the Oort constants A and B, which actually determine the motion of stars in the neighborhood of the sun and relate it to the rotation of the galaxy. Anyway, the bottom line is that you can measure all the individual motions of all the stars and take a kind of average. And that is called the local standard of rest. It's an important concept. The local standard of rest is if you measure all the neighboring stars with regard to the local standard of rest, then what you're seeing is their individual motions, because the local standard of rest itself is the motion of all of them around the galaxy. I'm putting this very badly, but the local standard of rest isn't a standard of rest at all. It's the the right velocity around the center of our galaxy for stars at our distance. That's basically what it means. And so just to cut to the quick, or cut to the chase, I beg your pardon, wrong metaphor there, cut to the chase in Richard's answer. Yes, he's right, or Richard's question, he's right, that the stars have their own individual motions. But on top of that, or underneath that, perhaps, they're being carried along by the rotation of our galaxy. So that it's like, I don't know. I mean, one way of putting it is to imagine it being a river flow with lots of people in rowboats rowing around on the river flow. They've all got their individual motions, but they're being carried along by the river. It's exactly the same.
Yeah, or a lotto machine where you've got balls inside a big ball and you spin the big ball and the little balls all do their own thing. Not quite, because they're being dictated by the rotation of the external ball. Anyway.
What's a lotto machine again?
I don't know. I tried.
No, it's good.
All right.
Yeah, I think stick to the river.
Yeah, the river's a good concept. I think we've used the river concept before.
We have, yeah, on a larger scale, because it's the way we envisage the way galaxies move. Galaxies also have their own motion as they're carried along by the Hubble flow, the expansion of the universe. So
all right. Thanks for your question, Richard. And finally, our last question for this week's episode. This is a question that comes from Paul, north of the border, and I'm assuming that means he's in Queensland, which could explain a lot about this. Paul has sent us a question. We've received in a format never, ever before done on Space Nuts. And I won't spoil it by telling you what he's done. I'll just hit the button and, let it go. Here we are.
G'day, Andy. G'day, Freddie. Hope this finds you going steady. No, not like those ancient Grecians. Struth, it's good to hear your audience is increasing. Now I got a little query, and I hope it's not too dreary. It involves event horizons and a spaceship and its chances of surviving. I know we can use a planet's gravity to boost our rockets and throw them outside its grip and speed up on a parabolic trip. Could you use a black hole's massive gravity to up a ship's velocity and hurl it closer to the speed of light? I know it's a kind of a long shot, and even if you hit the sweet spot, would go and pass one, make you faster, Or would you just end up like your mama's pasta? Dearest Freddie, darling Andy, love your show, it's really handy. So from up north of your border, this is Paul who's suffering from space nuts disorder.
Oh, man, that is brilliant. That is brilliant. Wow. Never, ever had a question sent to us in that format ever before. But thank you, Paul. That was so good. Now, Fred, you know that music. I thought it was something else. Well, actually, I think it's what I understood it to be was adapted from something much more classical.
That's right. Yeah, the tune is from, it's actually the Dance of the Hours, or Danza delle Ore in Italian, which is a ballet in Act 3 of La Gioconda, the opera by Amilcare Ponchielli, composed in 1876. And it's something I've known since I was...
Fred was there.
Well, I'd known it since I was a kid, because among the old 78 RPM records we had at home, that was one of them. And in fact, many years ago, I transcribed them all to digital format, and I played it last night just to remind me the quality is rubbish, sound quality, but the tune is there. And of course, it was heavily modified for Camp Granada, wasn't it?
Yes, that's right. Yeah. Hello, mother. Hello, father.
That's the one. Now, something that I should confess, Andrew, which only a few people know, is that whenever I listen to music, particularly a song, I never listen to the lyrics. It's always the underlying music. And so if I hear a rock song that I like, it's not the words, because I don't hear the words. I just hear the music.
Isn't that interesting?
Or folk or whatever it is, it's always the music. And so I was so captivated by the music there that I didn't really properly hear Paul's question. But I think it was about
I think I can nutshell it. He was asking, he was saying, like, we can get gravity assist through slingshotting around planets. Could we do it by using a gravity assist on a black hole, or would we get spaghettified?
I thought that was it. Yes, I got the impression it was. So the way to avoid being spaghettified by a black hole is to go past it sufficiently.
To never go to Queensland.
Never go near it. That's right. I do. By the way, there was a nice allusion. I did listen to the words at the end because I thought I'd better listen to this. Very nice lyrics, Paul. And I like the allusion to his mother's pasta, which of course is spaghetti. Very good. Yeah, being spaghettified. So if you're going past it fast enough, then you won't get pastified. You won't get turned into spaghetti, because you basically just whiz by it. And that's what happens to the star S2, which is the closest star to the supermassive black hole in the center of our galaxy. And its orbit is certainly being influenced by the black hole. But whether you could use that for a gravity assist is a question that I suspect has a negative answer. Because as I understand it, and I should really check this, but I think it's not so much the mass of a planet that lets you do a gravitational slingshot by flying by it. It's the way that mass is distributed. So you've got something, you get close enough to it that you're feeling mass from, you're feeling the gravitational attraction, not just of the planet as a whole, but of different parts of it. And they are what affect your ability to transfer momentum from the planet to the spacecraft. Now, with a black hole, by definition, its mass is all concentrated in a single point. So I suspect that might preclude the idea of using it as a gravitational slingshot. But it's something I'd like to try and check with my colleagues.
Okay.
And you can bet your life I'm going to listen to that again, because it's such a brilliant, and the lyrics are very, very nicely done.
I'm very sorry to say that if we were to try to slingshot round a black hole with Paul, all would be lost. But I think the ukulele would survive.
Well, it might go up in pitch because you've got a gravitational time dilation.
Yes.
I don't want to steal Paul's thunder here, Andrew, but I might just give a quick shout out to another musical genius who was in touch with us recently, and we never got back to him, and I hope we can at some point, and that's Jesse James Allen, who wrote essentially a symphonic work
that's right,
celebrating the Cassini mission, which is something very close to my heart. And so it was the Cassini Tribute. In fact, it's on www.cassinitribute.com. Brilliant stuff. Jesse James,
brilliant.
Fantastic. On the other hand, what we've just heard from Paul is no less brilliant in its own way, even though, that ukulele there, pretty great stuff. Maybe doesn't compare with a synthesizer reflecting an entire symphony orchestra. Never mind, it's all good stuff. It's all music. That's my view. It's fantastic.
I got one more surprise. Seeing you mentioned Cassini, Fred.
Okay.
Yeah.
Oh no.
Goodbye, Cassini. Your mission's finished.
I'll save you from that.
Yes. Yeah, that was somebody with a voice not very different from the one you're listening to now. So I too was inspired by Cassini, and somebody wrote that it's from La Donna Immobile. It's the tune, which is another operatic piece, and the Planetary Society commissioned somebody to write some words, but they only wrote one verse, and that was the start of it there. And so I wrote another two, I think, and I did perform it around the time quite a lot in for talks and things like that. And in fact, it was in South Australia that recording was made. So that was my one contribution, which is somewhat less musically talented than Paul's ukulele, and a lot less.
I have been waiting for a perfect opportunity to use it. So.
Yeah, okay. There you are.
Been sitting there for months.
Fell right into that one. So
you sure did.
It's on YouTube anyway, if anybody wants to hear the rest of it.
Yeah, Goodbye Cassini it's called, isn't it?
Yeah, that's right.
There you are. Well, we don't usually have a musical show, but it's been really really delightful today. So thanks to everybody who contributed. Thank you, Paul. Lovely to hear from you. I was going to use... because we had two Pauls on the show today, I was going to say it's an appalling show, but it wasn't.
No more appalling than any of the other ones.
Oh dear. Anyway, thanks for all your questions. Thanks for contributing to Space Nuts for another week, and we got so many questions, Fred. We're going to have to probably do this again in the not too distant future. So we'll catch up with everybody real soon. Thanks again. Thanks for listening. Thank you, Fred. As always, it's been great fun.
Yep. Good to be here, and thank you for your wit and humour in the meantime.
Dark humour as it is sometimes. Yeah. All right, we'll catch you next week, Fred. See you later.
Sounds great. See you.
That's Fred Watson, Astronomer at Large, part of the team here at Space Nuts. Thank you for joining us, and we look forward to your company next week. Until then, bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.